Yeah, I mean, I'm not sure, but I'm still going to go over it right now.
Okay.
Figure that out at another time. But thank you for telling me. And I didn't see the email yet, but I'm sure I'll see it. So let's go over that. You should be able to see it now, Zoe. So you should be able to still be able to log in. Well, yeah. Tell me, log in. Everybody should log in, and then Zoe, you can tell me if you see it now. All right. I already am presenting my screen. All right, let's do it. So the first question is an artificial satellite. I will make a comment that anything that orbits something else is really considered a satellite. It can be artificial, it can be natural, but even our moon is considered a satellite. And the sun would consider all the planets satellites. So I'm just pointing out, generally speaking, in day-to-day stuff, when people say satellites, they're normally referencing artificial satellites for telecommunications and TV and phones and military and all the other applications. Just pointing that out, that even natural, because you could technically get problems that reference satellites, and end up talking about a moon. So, anyways, an artificial satellite in this case orbits Earth at a speed of 7,800 meters per second at a height of 200 kilometers above Earth's surface, which that's not too far off from space station. It's a little less than the space station. Space station is 200 miles above our heads. That's the orbital path, at least for the space station. That's about 120 miles, 200 kilometers. A little higher than that will be the space station. But anyways, that's the height, that's the speed. The satellite experiences an acceleration due to gravity of. All right, so we need to kind of think about yesterday's lesson. The idea that on a planet, the value of 9.8 meters per second squared that we observe is only along the surface, because again, anywhere along the surface, you're the same distance from the center. And the strength of a planet's gravity really is dependent upon how far away you are from the center of the planet. And we also had been taught yesterday that out here, if you were an astronaut, that G would not be 9.8 out here. G would be less than 9.8 out here. And how much less? So it depends on how far. Further and further away, less and less. Never zero. I will point out that it's never zero. So gravitation is a force that extends throughout the entire universe for a single object. Even your own gravity force technically extends throughout the whole entire universe. It's not very large because your mass is very, very small. I mean, you could certainly calculate G for your G using this same formula, and I guess you'd have to kind of think, well, what shape would I be at? What would R be? I don't know, to be honest, but maybe imagine that your small little sphere of radius 1 meter and put your mass in there, and you can calculate your G. Of course, it's extremely, extremely small, so small that all things in the universe won't feel it. But for big planets, of course, it's significant. And I'm just pointing out that G goes for a planet, it literally extends all the way out into the entire universe, always getting less and less in strength as you get further and further away. But it's never zero. So if you were to graph G versus R, the strength of Earth's gravity, G, at a variety of points, R, further and further away. Again, we talked about this relationship. It's an inverse proportion. And that would therefore cause it to have a shape that's something like this. This is an asymptote, by the way. The horizontal axis is an asymptote, which means that these data points that numerically represent what G is at a further and further distances would get closer and closer to the x-axis. Because if that graph literally touches the x-axis, that means you're finally at a position where G is zero. Like if this graph intercepts the axis here, and that's the x-intercept, then you'd say, okay, out at this distance R, the value for Earth's gravity is zero. It never does. It's an asymptote. That's the idea of an asymptote. An asymptote in math is the idea that you have a vertical or horizontal asymptote. In this case, it's a horizontal asymptote. And the graph is going to approach that value of zero, but never cross it, which is mind-boggling to think, how can something approach something forever but never reach that point? How can you approach the door forever but never reach the door? It's called a paradox. I think it's called Olber's paradox, which is interesting in itself. But mathematically, it's technically true that something can mathematically approach some point but never reach it. So when you think about carrying this value all the way out really, really far, because you're getting so far away from Earth, Earth's gravity gets tinier and tinier. G would be 1 at some point, 1 meter per second squared, 0.5 meter per second squared at some point out there, 0.1, then 0.01, then 0.0001, and 0.00000001. And you can go so far away that Earth's gravity is almost 0, but shockingly, if you had a subtle and gentle enough experiment way out there in outer space, you could determine that when you let go of something, it's still slowly starting to drift towards Earth, even though Earth is that far away, indicating that Earth's gravity is still out there. It doesn't ever hit 0. So knowing that will help you answer a lot of these questions, because in a lot of the questions, one of the choices is G is 0. G is never 0. There's no place where G is 0. So that is a helpful thing to know. And mathematically, that's supported by this graph, that being an asymptote. It can approach 0, but only at infinity. And if some of you are in higher level math classes, you're learning about limits. I don't know if you are. Some of you probably are. And that's the concept of the limit. In this case, as R approaches infinity, G approaches 0. And in the limit, when R actually is infinity, which practically speaking, you'd say, is that even real? That's one of the philosophical questions you have to deal with as a physicist. You have to say, well, mathematically they deal with infinities. How do we interpret that in the real world? Is it just a mathematical tool that we use, or does it have real meaning in our real world? Is there anything that's really infinite? I don't think so, but that's a philosophical question. I personally don't believe it's real at all. I think it's just a useful mathematical tool. But know that technically in that limit, if you could get infinitely far away from Earth, whatever that means, I don't even know, that out there your G meter would read 0. But anything less than infinitely far away, it will not read 0. Okay. So with that said, erase all that. Let's look back here. Boop. An artificial satellite orbits Earth at a speed of 7,800 meters per second. As we said, it's up higher, up in the air, about 200 kilometers above the Earth surface. The satellite experiences out where the satellite is, experiences an acceleration due to Earth's gravity of A, 39. It cannot be more than 9.8. A planet's gravity is always strongest on its surface. Another interesting question is, what if you start digging a hole? If you dig a tunnel to the center of the Earth, what happens to G if you do experiments throughout that tunnel? Surprisingly, you find that G actually decreases. The closer and closer you get to the center of the planet, if you had a tunnel that went down to the center of the planet, G gets less and less and less, and it reaches a value of 0 at the center of the Earth, mathematically. Can we ever test that? I doubt it. We're never going to end up in the center of the Earth. Mathematically, it says it should decrease to a value of 0 inside the Earth as you go closer to the center. The maximum value for G is on the surface, and then as you go further into outer space, again, it gets less and less and less and less and less and less. So my point is, it can never be anything greater than surface gravity. So G definitely can't be 39 for Earth. It's nowhere in space is the value for Earth's gravity 39. It's 9.8 or less. Less than 39, that sounds good, but greater than 9.8, no, it's never greater than 9.8. So A and B are out. C, 9.8. That's only on the surface of the Earth. C is out. D, less than 9.8, that sounds good, but greater than 0. Sounds good. That's right. D, 0. You'll notice, again, the knowledge that gravity is never 0 will help you at least cross that out. Nope, it's not 0. And I mentioned yesterday that I, for some reason, wasn't sure if it was 4 or 5. Years ago, these used to be A, B, C, D. I think 2 years ago, they made the change to go to 5. So it is 5 choices, A through E. I couldn't remember for some reason. But anyways, that answer is D. Let's move on to the next one. A meteoroid. It's just like a meteor. Think of a meteoroid, I guess. Maybe they're assuming it's kind of circular, but probably not. But either way, a meteoroid is the one it's a meteor once it lands on the surface of the Earth, and they call it a meteoroid when it's still in outer space. I have no idea why. But anyways, a meteoroid is in a circular orbit this distance away from the surface of a distant planet. The planet has the same mass as Earth, but has a radius that's less than Earth's. Its radius is only 90% of Earth's radius. All right. The acceleration of the meteoroid due to the gravitational force exerted by the planet is most nearly again, the acceleration of the meteoroid as it goes around the Earth due to the gravity force exerted by or not the Earth, but this planet, is most nearly what value? So first we'd have to kind of reference that formula for G. I do recommend storing this one to your brain. It's useful for all these questions. Remember, if you don't remember it in the AP exam, you can just think, well, this is a gravity force formula is equal to another gravity force formula. These are two equations for the same thing, the gravity force. And now you're back down to that formula. But it's worth remembering it. So it's saying that G is, remember, inversely proportional to R. So we know that if the radius is less for this planet, then G has to be actually more. The radius of this other planet is smaller than Earth's. That means, and it has the same mass, they also said. So if they said there was a mass difference, then you'd have to consider the relationship between G and M. But they said that the mass of this other planet is the same as Earth. So there's no, the difference in G between Earth and this other planet can't be due to the mass because they have the same mass. G is just a constant. So we're just looking at, again, the differences here. If the radius is smaller, it means that it's more condensed. It's more compact. It's more dense. And therefore, R being small, again, inverse relationship, R smaller, G is higher. So this planet must have a G value that's greater than 9.8, which tells us it can't be A and it can't be B, because the only two numbers that are greater than 9.8 are 10. Which way does this gravity pull? Always towards the center of the planet. For that reason, our answer would be C. Question 3, a moon of mass 10 to the 20th kilograms is in a circular orbit around a planet. The planet exerts a gravity force of 2 times 10 to the 21st newtons on the moon. All right, the centripetal acceleration of the moon is most nearly, make sure we understand what we're being asked. We're asked to solve for the centripetal acceleration. For most students, they might say, ooh, I remember there's a formula for that. In fact, it's on your equation, your AP equation sheet. You have this. But then you look back at it and say, they didn't give me speed. They don't give me R either. So I have to be clever about this then. Is there another relationship that involves centripetal acceleration? If you just remember F equals ma in general, technically F nat equals ma, then for circular motion, you say the centripetal force on the orbiting object, which is the moon, is equal to the mass of the moon times the centripetal acceleration of the moon. They did give us how hard this planet is pulling on the moon, right here. Remember that the gravity force is the centripetal force. This is the moon out here, and it's going in that circular path. That gravity force, it is the centripetal force. It's pointing towards this, pulling inwards towards the center of the planet, causing this moon to go in a circular path. So since they gave us the gravitational force, we know that that number can go right here because the gravitational force between those two planets is the centripetal force. And technically, we can solve for the centripetal acceleration as long as we know the mass of the moon, which we do over here on the left. Sorry. And the force. So it's the ratio. So when we solve for A, the centripetal acceleration, we get force divided by mass. The force is 2 times 10 to the 21 divided by the mass of the moon, which is 10 to the 20th. 2 divided by 1 is, and these are factors, right? People writing it like this makes some students forget that these are factors. This is 2 is a factor times 10 squared, which we know is 100. I'm sorry, times 10 to the 21st. But it's a factor. 1 is a factor, 10 to the 20th is a factor. So we can just look at it as 2 over 1, which we know is 2. And now we're looking at what would 10 to the 21 divided by 10 to the 20th be? Well, how many extra are on top? 1. Or you can imagine shifting the 10 to the 20th up as 10 to the minus 20, right? And you'd end up with 10 to the 21 times 10 to the minus 20. And then you add the exponents if you want to think of it that way, and you'd end up with 10, right? 10 to the 1. But there's an extra 1 on top. So we end up with an answer of 2 times 10. 10 to the 1 is just 10, which we know is 20. So that tells us the centripetal acceleration for this moon, based just on this information, must be 20 meters per second squared. That puts the answer as C. Next question, question 4. A 2-kilogram object is at a distance 10 million meters away from the center of the Earth, which has a mass of nearly 6 times 10 to the 24th kilograms. What is the approximate gravitational field strength of Earth's gravitational field at the location of the 10-kilogram object? Remember that G is the gravitational, it's called the gravitational field, because it's the concept of a force field. A force field, like in Star Wars, surrounds somebody, and then somebody comes and they get zapped by the force field. There's the way where you hear about fields, I guess, from Star Wars, right? And it means that there's some force on the person when they enter the force field, but the person creating the force field, or if it's a machine that's creating the force field, causes a bubble to surround it. There's a force on the person when they enter the bubble, but that machine that's making it isn't touching them. That's the concept of a force field. You can put a force on something without being in contact with it. Gravity works that way, magnets work that way, and electric charges, positive and negative charges, work that way as well. You can put forces on each other, push and pull on each other with great distances between them. So when you hear gravitational field strength, we're talking G. They're asking, what is the value for G? What is the value for G at this location? A 2-kilogram object, again, is 10 million meters away. And they gave us the Earth's mass. What is G? 10 million meters away from the center of the Earth. That's what they're asking us. Well, G for Earth is depending upon the mass of the Earth divided by how far away you are from the center of the Earth. The relationship, G is inversely proportional to 1 over r squared. Now, if they made it nice for us, they would have made this the number 12 million and said, well, if you're 12 million meters away compared to and that I'll also point out, they didn't give you the radius of the Earth, surprisingly. You could have Googled it. They also gave it in number 2, I think. But the radius of the Earth in number 2, I think it was number 2, they told us was 6 million. 10 to the 6th is the word million. Surprised they didn't provide it here, to be honest. So if this was the number 12 million, and we know that currently we're at a distance 6 million, then that would be a nice number. You go, okay, 6 million goes into 12 million, 2 times, so you're 2 times further away. 2 squared tells us that G will go down by a factor of 2 squared. It'll be 4 times less. 10 divided by 4 would put us at 2.5, and even if that was an approximation, you'd select A, close to that. To do it exactly, well, you'd have to figure out how many times bigger is 10 million than 6 million. Ten divided by 6, how many? Essentially, it's the same answer as how many times bigger is 10 divided by 6. 10 divided by 6 on the calculator, I get 1.6. So that means the distance in this problem is, this distance of 10 million meters is 1.6 times further away than you are when you're living on the surface of the Earth. Well, we could technically apply this exact same proportion and do the same old rigmarole. If r increases times 1.6 by a factor of 1.6, G will decrease. Again, these are inversely proportional times what factor? If there was no square on r, it would just be times 1.6, which means divide it by 1.6. But there's a square there, so it's times 1.6 squared. Got to get out my calculator. 1.6 times 1.6. Enter. I get 2.5. So that means G out there, which is what they're asking us, at 10 million meters away from the center of the Earth, will be less than 9.8 by what factor? 2.5. And we say less than, we mean you have to divide this by 2.5. So you'd have to type in 9.8, divide by 2.5. If you were doing this all exactly, I already think this is too much for a multiple choice question. You need to get through these, so you got to be able to estimate it. I actually did that in the beginning. I would have selected A and moved on. But if you did it exact, 9.8 divided by 2.5, I don't know, divided by 2.5, I get 3.92. They don't even want you using 9.8 on the exam. They want you using 10. 10 divided by 2.5 brings us to an answer of 4. In fact, actually, I think, did I originally estimate it as 2? Wonder why. 2.5 times less. Would have been 4. Yeah, the answer is 4. I don't know why I said that. Oh, because of the square. I forgot about the square. Yeah. So ignore my original thing. I had said if it was 12 million, then it would have been 2 times less. But it's 2 squared, so it's 4 times less. All right, moving on to the next question. 4 times less than 10 is pretty close to 2. All right, next question. Space station has a mass of m. So there's a space station, and there's the Earth. All right. What question are they asking? A payload. A payload is when they deliver something to outer space. Something gets sent out there. Maybe it's food or something for them living in the space station. The mass of this food or whatever they're sending out there is less than the mass of the space station. Thank goodness. Otherwise, that would be a difficult transfer. Soon after, the space station adjusts its orbit so that it's a little further, 50 kilometers away, but a little further away from Earth's surface. So after this food is delivered to the space station decides to come out a little further from the center of the Earth. All right. What's the question? Which of the following best describes the effects of these 2 changes? One, that there's more mass on the space station because they delivered some food, let's say. And the other thing is that they moved a little further out. Which of the following describes the changes that would cause on Earth's gravity field? G. G doesn't care about anybody or anything. A force field doesn't care about who's out there or how heavy you are. It's just a field strength. It's that value in that spot, regardless of whether anybody's there or not. If everybody in the whole universe disappeared from the surface of the Earth, and we found out that at this distance, G is 6.7, and the whole universe disappears other than Earth, the value at this point for G is still 6.7. Doesn't matter who's out there. So the increase of mass has no effect at all on the field strength. The increase in the mass has no effect. That's true. Because G only depends on the mass of the Earth and how far away you are from the Earth. And the increase in orbital radius going a little further should decrease the field strength. Yeah, a little further away means gravity for Earth should be a little less there. A. Number 6, a satellite of mass 1,000 kilograms is in a circular orbit. The centripetal acceleration of the satellite is 5 meters per second squared. What is the gravitational force exerted on the satellite by the planet? Looks like we're in another scenario where we can use this. That's just my thinking right now. Just have to remember that the inward force, the centripetal force, it is the gravity force again, right? If the planet's out here or the planet's underneath and this is the moon, this inward centripetal force is the gravity force. They are one and the same. So that means if they're asking us for the gravity force, we can just solve for the centripetal force. How do we get that? As long as we know the mass of the orbiting object, which is 1,000, and the centripetal acceleration of the orbiting object, which is 5, then just multiply them. 5 times 1,000. 5 times 1,000 is 5,000. It's an inward centripetal force on that satellite must be 5,000 newtons. C. 7. Planet X has twice Earth's mass and 3 times Earth's radius. These can be challenging questions, but I'm getting the sense as I review a lot of students' work that you guys are getting better at this. Some of you are getting a lot better at this, and that's good because this is hard. It's an awful lot of college students that still can't even do these. So you're developing good skills. This is a question about G, and it's about a new planet, planet X. Remember, G on the surface of any planet is proportional to the mass of that planet and the radius of that planet. And they're comparing planet X to Earth. They said the planet X has twice the mass. If that's all they said, and they didn't cross the 3 times Earth's radius, planet X has twice Earth's mass. What is G on this planet, on the surface of this planet? G is proportional to the mass of the planet. If it's got twice as much mass, G is not 10, but 20 meters per second squared on the surface of the Earth, twice as much. If that were the case, if that was the only thing. G increases time, the mass increases times a factor of 2, G would increase times 2. However, there's another effect. This planet also has a radius that's 3 times greater. So now we have to think, how is the relationship, what's the relationship between G and R? That's an inverse relationship. R is increasing times a factor of 3. It's 3 times wider than Earth. The radius is 3 times bigger. That means G will not go up, but go down because they're inversely proportional. If there was no squared here, if that was not there, then it would just be times 3. It would be a divide by 3 effect. But there's a square there. So we have to say times 3 squared, which we know is 9. So when we say goes down times 9, that means we have to divide by 9. So what is the combined effect? We had 2 effects. One causes it to go up times 2. The other causes it to go down times 9. Effect 1, effect 2. What is the combination of those? 2/9. So the surface gravity on that planet should be 2/9. Well, that's close to 2/10, and G is so conveniently close to 10. If it was 2/10 of 10, that would bring me right into this answer A. And that is the correct answer. It's 2. I'll also point out that the units, sometimes that might throw you off. You're thinking, if that's G, why isn't it meters per second squared? Just a quick comment that if you solve just F equals ma for acceleration and plugged in the units for force is newtons, the units for mass is kilograms. So sometimes they express acceleration in units of newtons per kilogram, like they've done here. It's usually meters per second squared, but sometimes it's newtons per kilogram. And what that means is for G on Earth, if we wrote it that way, 10 newtons per kilogram, it just means for each kilogram, it will have a weight of 10 newtons. So if you have a 1 kilogram thing in our classroom, what is the weight? 10 newtons. We remember it's m times G, 1 times 10, 10 newtons. If it had a mass of 2 kilograms, then, well, G is 10 newtons for each 1 kilogram. If it's 2 kilograms, well, it's 20 newtons. 2 times 10, 20. So you can think of G that way if you'd like. It's not common. Usually we just think of it as meters per second squared, but I didn't want you to get thrown off by those units. Just know that regardless of the units, if they say gravitational field, you know they're talking G. All right, I will, because there were 3 other questions. Well, I can actually do this last one really quick. This is the one you tried in class, I think, right? Yeah. This says the satellite is 2 times further from the center of the moon. So they're comparing how strong gravity is at this distance, 2r, where r is the radius of the moon. So if you're on the surface of the moon, it's got some value g, but now you're 2r away from the surface of the moon, an extra radius out, 2r. And remember, since we had an inverse relationship, I'll just do this last one because I know we're out of time. Since g is proportional to 1 over r squared, if r goes up times 2 from r to 2r, then g goes down times 2 squared, which is 4. Down, remember, down means divide by 4. That means the new value for g is out there is whatever g is on the surface of the Earth divided by 4. That would be A. In fact, if you could give me 1 or 2 more minutes, if you don't mind. If you have to leave, it's totally fine, because I'm recording this and I didn't record the last one by mistake, and I wanted to post this video, and I've only got 2 questions left. So if you feel like you need to go, totally fine. If you want to hang out just for another, literally take me about 2 minutes. I just want to complete the video. 9 and 10 are the last ones. On the surface of a, because you don't have anything, right? This is the last period. Yeah. On the surface of a spherical asteroid, a small object of mass, a really tiny object, 10 to the minus 5, right? That's 0.000. I don't know. You can count it out and draw it out. Something like that. If this was the number 10, 10 to the minus 5 is 1, 2, 3, 4, 5. So that's the number. So they're saying that the mass of this object is this amount, 0.00010 kilograms. Its weight is 1 times 10 to the minus 10, because it's, I mean, you're talking a speck, like a piece of dust, I guess. I don't know. But whatever. That's what they said, that you're on an asteroid and you're going to drop the speck. Which of the following graphs correctly shows the rock? Oh, I take that back. Well, the asteroid has very little gravity, has some. So it's not surprising that the weight would be very low because the asteroid's gravity is so low. But technically the mass is still so tiny. Well, I don't know. To be honest, I don't have a sense of that. 10 to the minus 5. Anyways, who cares? I'm overthinking it. So there's some rock, and those are the values. Doesn't really matter. They're asking, what are the graphs that would be correct that represent the motion of this rock when you drop it on the surface of this asteroid? This one is indicating that there's no net force. They said select 2 graphs out of the 4 graphs that would be correct. We know that's not true, right? When you drop anything, doesn't matter if it's on Earth or on an asteroid, the net force is mg. That's only for, if there's air resistance, then it's mg minus the air resistance. But if there's no air resistance, which they very rarely would say there is, then the net force is just your weight. The net force in this is saying it's 0. No, that can't be correct. So A is out. Would it accelerate towards the surface of the asteroid? As long as the asteroid has gravity, then yep, it'll be some amount of net force. And Newton said if any net force, it will cause an acceleration. So will it gain speed as it falls towards the surface of the asteroid? Absolutely. At a very impressive rate? Certainly not. A very slow rate, but it would little by little gain speed and as it fell towards the asteroid. B, check. C, would it have an acceleration? Well, I guess if we had to calculate it, what would we do? We would do F equals ma, right? A is the net force divided by the mass. The net force is just the weight. They told us the weight was 10 to the minus 10 newtons. 1 times 10 to the minus 10 is 10 to the minus 10. And they told us the mass is 10 to the minus 5. So what would the 10 to the minus 10 divided by 10 to the minus 5 be? The extra is on top, but it's an extra minus 5 on top, right? So that's a 10 to the minus 5. You could think of, again, bringing that up if you wanted, and you'd have it as 10 times 10 to the plus 5, and then you'd add those two to get 10 to the minus 5, right? So that result is an acceleration of 10 to the minus 5. Is that what they're showing? Here's our 10, here's our dot. 1, 2, 3, 4, wait. 1, 2, 3, 4, 5, 6. Huh, why are they showing 6? I have 10 to the minus 5. Huh, did they make a mistake? 10 to the minus 5. Yeah, they made a mistake. 1, 2, 3. Oh, no, I didn't. What was that? No, over here. Acceleration. They made a mistake. There's one too many zeros here, I think. I don't know. This is the correct answer. That would be, but for some reason, I think there should be 3 zeros there. 10 to the minus 5 is what I get. Anyways, that would be they said select 2. It's B and C. Shocked if they got that right. If they made a mistake there. 1, 2, 3, 4, 5. Yeah, they have 6. Huh. Oh, I'm making a mistake. It's not 10 to the minus 5. My apologies. 10 divided by 10 is not 10. 10 divided by 10 is 1. So the answer would have been 1 times 10 to the minus 5. And therefore, that the dot would go after the 1 right here. 1, 2, 3, 4, 5. Correct. Yeah, I'd be surprised if they made a mistake. I made a mistake. College board shouldn't be making any mistakes. All right, so the answer there was B and C. D, there's hoping that some students think that the gravity of the asteroid is still 10, because some students will think everything has a gravity of 10, but you guys won't. Only Earth does, only on the surface. This asteroid does not have a gravity of 10 meters per second squared. All right, so B and C were the correct ones. And the very last question, oh, yet another question like this. Now, you might get just like 1, to be honest. You know, out of your 4, or how many you get? 50 multiple choice questions. You get you more than likely will get 1 question that's like this, where it's like, here's a planet, and we're going to compare 2 planets, and one of them has a greater radius by this number and more mass by this number. What is the value of this other thing? I'm more than likely to get 1 of these, maybe 2, but I'd be surprised. A planet with half of Earth's mass. Oh boy, we're back to the same. A planet with half of Earth's mass, because we have to figure out what G would be on this planet, because they're ultimately going to ask us what this astronaut would weigh on this planet. And we remember that weight is m times g. So we need to work out what G is first on this planet, and then we'll go from there. So this planet has half the mass. So if the mass is going to go down times 2, G would go down times 2, just due to that fact alone. But there's another thing to complicate it. It also has half of the radius. So the radius is going to go down times 2, because remember, down times 2 means divide by 2, cut in half. So radius is half of the Earth's radius. That's R goes down times 2. G would go down times 2 squared, right? You're putting in a 2 for R there and squaring it then. So it's going to go down times 4. So what is the overall effect? The mass effect is dividing by 2. and the radius effect is dividing by 4. So what is the combined? If you cut something in half and then cut it into 4 more pieces, and then select 1, you actually end up with 1 out of 8, right? If you have 1 pizza and cut it in half, you've got 2 pieces, and then you cut those into 4 more pieces, you end up, I suppose, with 8 pieces. So it's 1/8. So G on this planet should be 1/8. So if he weighs 800 newtons on Earth, he would own, weight is proportional to G, right? Weight and G are proportional. So if G is only 1/8 of what it is on Earth, his weight should only be 1/8 of what it is on Earth. What is his weight on Earth? 800 newtons. What would 1/8 of that be? 100 newtons. A. Some of those are tough. I'll be honest, they're tough, and I didn't learn that overnight either. It took me a long time to practice these kinds of things. So if you're still kind of coming along, don't give up. But I am getting evidence that a lot of students are at least getting better at this. That's great. All right, at least I appreciate you hanging out for those extra 10 minutes. At least I was able to finish recording. I can post that for the other class because they didn't see 8, 9, or 10. All right, do you guys have any questions at all? Usually you don't. Kepler's laws, I'm just going to comment. That's the last part of the orbital motion piece you need to do in circular motion. It's called Kepler's laws. So I'm going to probably assign, it might be a CK12, something like that, or it might not. Maybe I'll just find a couple videos from Ed Puzzle for you to watch. We have to do that. It doesn't take long. It only takes one or 1.5 classes for me to teach you the concepts behind it. All the questions that come on the AP exam for Kepler's laws, multiple choice concept questions. So I'll teach you, I'll have something posted in Google Classroom for you to learn something over the weekend about Kepler's laws. And I'm just letting you know that there's only one last piece we have to do for circular motion. It's back to Earth, not outer space stuff anymore. We have to do some examples like going over a hill. Like if you're driving a car and you go over a bump, that as you go over the big hump, that's actually a curved part of the road, and that's circular motion. So you actually need to learn that something like that, about problems like that. Swinging something in a vertical circle, I have to kind of cover that. So there's a couple other so-called special problems that I still have to show you next week, but we shouldn't have any problem finishing it. More than likely, circular motion will be done by the end of Thursday. I am about to record, by the way, those 10 problems after my lunch. I have 10 more problems to finish from the forces quiz. And then I'll post it. The first 10 questions already were posted. I'll probably post them both again next to each other. So if you want to review those, and I might even include something on your assignment to do that, to look over your old quiz. And if you had whatever amount you had wrong, you should be able to access it right in AP Classroom. Type up something that shows that you reflected on that question and submit it as an assignment. More than likely going to have you do that because that's been my plan for a while now. So anyways, that's all I have to say. And then I guess the last comment is there is a Saturday session tentatively scheduled for January 30th, Saturday. Of course, Saturday sessions are always on Saturdays. Tentatively scheduled again because I haven't got a full confirmation from the person that coordinates that, but that's what we're shooting for. It would be obviously virtual again, 8 to 12. I obviously will give extra credit again. So just keep that in mind. I'll let you know when I have the definite day, but should be.
And when do you think the test on this unit will be?
Probably over the weekend. I don't think I'm going to give tests in class anymore. We just don't have time for it. I'm going to give you take-home tests. I'm just going to let you take it over the weekends. It'll be an AP Classroom, and you log in and do it. Okay. I mean, think how much time we lose, right? I mean, in a year like this, I have to start making changes. There's no way. If I gave you like 5 more, whatever it is, 4 more tests, and I have to now lose 4 more classes just to have you sitting in my class taking a test, I can't do that anymore. So to stay on that track, because I'd rather actually have more time at the end of the year to review, right? You really want at least 2 weeks. Joey, you only got 1 week with me, right? You only had 1 week, I think.
Yeah, wasn't much at all.
I'd really like to always have at least 2. It's my goal to just be done with everything, and let's just spend 2 weeks reviewing everything and giving you a practice problem. So that's what I'm going to do. I'm going to give take-home exams so that you can do them over the weekend. So more than likely it'll be next weekend.
Okay.
All right. Any other questions? All right, guys. I hope you all have a great and wonderful weekend. I'll see you next week. Bye-bye.
Mr. Garzak, have a good weekend.
You too, Jaden. Bye bye.
Thank you. Bye bye.
Bye bye.